right, so we're doing scientific notation word problems today. They're going to start with really simple ones, and then towards the end we'll have to figure out what operations we're using. So let's start with number 1.
1.
In Australia, the people use approximately 2,240,000,000 pounds of bread in a year. That's a lot. How can we write this number in scientific notation? So this one, all they want us to do is take this number, write it in scientific notation. So we just take our decimal, count 1, 2, 3, 4, 5, 6, 7, 8. Did I count that right? So 10.
It should be 9.
It should be 9. I'm thinking that too. Yeah, because it's going to be 3, 6, 9. I'll just count it by threes. So I know it's 10 to the 9th. And then the decimal in the front would be just 2.24. And we leave off all of the zeros. So it's possible you can have word problems where all they want you to do is to write it in scientific notation. This is definitely shorter than that is.
We are.
Okay. Okay, on number 2, it says, if a satellite travels 62 million miles from Earth, how can we write it in scientific notation? So, I'm going to go 1, 2, 3, 4, 5, 6, 7 places, so 10 to the 7th. And it would just be 6.2 for my decimal, and that's it. So just doing regular old scientific notation. On number 3, I'm trying to think how you would say this. Tens, hundreds, thousands, 10,000ths, 100,000ths, millionths.
65 million.
65 millionths is the wavelength of yellow light. Can you express the measurement using scientific notation? Now, what's going to be different when we start with a decimal and do scientific notation? It's going to go to the right, and our power is the negative. That's right. 1, 2, 3, 4, 5. So I stopped between the 6 and the 5 to make it 6.5, and we jumped 5 places. Since this is a decimal, our power is going to be negative 5. Anytime you have really small numbers, this is going to be a negative. The really big numbers, like these up here, the power will be a positive. All right, now we're going to start getting into some where we have to actually do operations. They're going to ask us for more. On number 4, it says the bedroom of our house is 1,200 cubic meters. So cubic meters is like the volume, like they're looking at how much air fits into the bedroom, not just the floor space, but like how much space there is in the room. We know that there are 3.4 times 10 to the 9th particles of dust per cubic meter. Right? How many particles of dust are present in the bedroom of our house? So what operation would we use here? Just pretend this is a normal number. Huh? Multiplication. So what I'm going to do first is write 1,200 in scientific notation. So I'm going to take it 1, 2, 3 spaces to the left.
That's
So one.
a pretty big bedroom.
I don't know. 1.2 times 10 to the 3rd. Yeah, this is.
Yeah, I know.
That's not that big still.
It may. I don't know.
Yeah,
We'd have to think about it.
Meter.
All right. So that is the scientific notation for the size of the room, and then we're going to multiply that by the dust particles. Shh. We are recording, guys. Shh. Okay, so we're going to multiply that by the amount of space, the amount of dust that's in each cubic meter. So this is the number of cubic meters in there. This is the dust per cubic meter. When we multiply decimals, you have to multiply the decimal part together, and then you put the powers of 10 together. So 1.2 times 3.4 we're going to do on the calculator. It comes out 4.08. Sometimes they'll go ahead and round that to 4.1, so it'll look like these. And then what would the power on 10 be?
You know, 12.
12, because we're going to add the 3 and the 9 together. Good. So that's how many dust particles would be in the house. And we can figure out if this is a big bedroom by considering the ceiling is usually about 8 feet. So I take 1,200 divided by 8. That's 150 square feet. It'd be like 10. It'd be like a 10 by 15 room. It's a fairly good sized bedroom, but not like huge. It wouldn't be
No,
the
but it's
size.
cubic meters.
Right. Oh, meters. Yeah, in meters it might be. I was thinking feet. That would be a pretty good sized bedroom. It's like must be the master. All right, let's look at number 5. Find the weight of 6 billion dust particles if a dust particle has a mass of 7.53 times 10 to the negative 10th grams. So a dust particle is evidently very tiny, set 10 to the negative 10th. So 6 billion, first I got to think of that as a number. So how many zeros are on a billion? So there's 1,000, there's million, there's billion. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9. So it'd be 6 times 10 to the 9th. And then, so that's 6 billion dust particles, which is less than what was in this bedroom, by the way. And each dust particle has a mass of this, so we're going to multiply 7.53 times 10 to the negative 10th. So first you're going to take 6 times 7.53. We get 45.18. Sometimes they'll round that off to 45.2. And then when we add the powers of 10, I'm adding 9 and negative 10 together, so it will come out negative 1. Now, is this scientific notation?
No.
No, what's wrong with it?
There's 45 there.
45 there. It's bigger than 10. So I need to move this over. So if I move this over this way, that means I'm going to be multiplying it by another 10 to negative 1. I get 4 point, I'm just going to round it off to 4.5 because there's a lot of decimals there we probably don't need to keep.
So there's
And then 10 to the
4.5
10 to the
grams
negative
in
2.
6 billion particles.
Well, it's 4.5 times 10 to the negative 2.
No,
So,
but wouldn't you add one? Because it's not division, it's multiplication.
oh yeah, we should be adding one. So that should come out, it should be positive 10. That should come out to the 0. So it would be 4.5 grams. He's not wrong.
Oh, you couldn't have a 0 and 10.
Yes,
Yeah, you can. If you're making it scientific notation. You could just leave it off. That'd be the same thing as 4.5 grams, which is not a lot. A gram weighs about a paper clip, so it's like 4.5 paper clips
Yeah,
worth
but
of dust.
like a speck of dust.
But that'd be a lot to breathe, I suppose. All right, thank you for catching my mistake. All right, so let's go ahead and look at number 6.
we're so fragile.
It says, shh, we're recording, guys. Last month, my friend bought a computer. If it can perform 4.66 times 10 to the 8th calculations per second, what is the performance of the computer in 1 minute? So tell me how we're going to figure this out. This is how many calculations there are per second. How are we going to figure out how many there are in 1 minute?
Multiply it.
Oh, you're going to multiply by 6.
Multiply it by 60. So I need to put 60 in scientific notation. What is 60 in science?
Times 10 to the first.
6 times 10 to the first, because I just have to take the decimal back one place. So I'd have 6 times 10 to the first, and we're multiplying it by 4.66 times 10 to the 8th. So if I take 6 times 4.66, we get 27.96. Sometimes they'll go ahead and round that off to 28, since we didn't have that many decimal places over here. And then what's my power of 10 to start with?
To the 8th.
To the 9th, because I got to add 1 and 8 together to get 9. And then this is not scientific notation because 27 is bigger than 10. So I have to move that over, and that'd be 2.796 times 10 to the first times 10 to the 9th.
2.7 to the 10.
So I think we'll round it off to 2.8. I'm getting tired of writing all those decimals. And then 10 to the 10th. A lot of times if there's not as many decimal places on one of these, they will round it off more. I've actually, if we did significant digits, which you get into in high school science, they would have rounded this off to just 3. Because the 6 only had 1 digit of accuracy. But you'll learn about that in high school.
No.
Alright, number 7. If the speed of light is 3 times 10 to the 8th meters per second, How many seconds does it take light to reach the Earth if the sun is 1.5 times 10 to the 11th meters from Earth? Write the answer in scientific notation. So the speed of light is 3 times 10 to the 8th meters per second. It wants to know how many seconds it takes to reach Earth if this is our meters. So what operation are we going to be using here?
Division.
Division. This is your velocity, and this is your distance. So do you guys remember the velocity formula? Velocity equals distance divided by time. And you can actually rearrange this. We're actually looking for time. So time, yeah, if we rearrange that, time would equal velocity over distance. There's that little graphic organizer you guys had. So we're going to take this velocity, the 3 times 10 to the 8th, and divide it by 1.5 times, no, I did that wrong.
No.
I think this is not right either. So hang on.
Yeah, it is. It's right. Because think about it. Because that's
right.
the distance.
I think it's got to be distance divided by velocity. So let's think. So
Oh,
distance
divided by
equals the velocity times the time. So that means distance divided by velocity would be equal to the time. So if we're looking for time, we've got to take the distance, 1.5 times 10 to 11th, and divide it by
It was so
the
much
velocity.
easier the other way around.
Well, the decimal was, but the powers weren't. So if I take 1.5 divided by 3, I get 0.5. We'll fix that in a minute. And if I have 10 to the 11th over 10 to the 8th, what do I do to those powers?
You use the
Subtract. So I'm going to get 10 to the third. Do I need to fix anything?
Yes.
Yep.
Yeah, this needs to move the decimal place over 1. So that'd be 5 times 10 to the negative 1 for just this part. And we already had 10 to the
It
third.
gets 500
So 5 times 10 to the second. And then seconds. And so it says to write the answer in scientific notation. I did. But you could also figure out, just for real life purposes, that that's 500 seconds. And you could divide that by 60. So if I take 500 divided by 60, this would be about 8.3 minutes. That's how long it takes the light from the sun to get here. So if something happened to the sun and it suddenly disappeared, we wouldn't know for 8 minutes. Because it takes 8 minutes for the light to get here.
Talking about that last week.
And then your stars, the stars are even further away, so it takes hundreds and hundreds and thousands of years, sometimes millions of years for the light to reach us, so it would take us a really long time to know if a star had burned out because they're so far away. Okay, on number 8.
Oh, the star burned out in 2000 BC.
Yep.
And
According
just
to
like
scientists, the Earth's mass is 5.98 times 10 to the 24th kilograms. So I'm so thankful we're not writing all of those zeros.
God.
The mass of the sun is 1.989 times 10 to the 30th kilograms. How many times greater is the mass of the sun than the mass of the Earth? Write the answer in science. So we're comparing the sun to the Earth. If I want to know how many times bigger the sun is than the Earth, I have to divide them. Now, this is part of our standards. Part of what you guys are going to be tested on is being able to compare how many times larger one thing is than another in scientific notation. So we're going to take the sun, which is 1.989 times 10 to the 10th, and divide it by the Earth, 5.98 times 10. I'm sorry.
You do the 30th, not the
30th. Yeah, I was like, I did something wrong. To the 24th, and we're going to divide them. So if I divide this number by this number, I get like 0.33 repeating. And then 30 minus 24 would be 10 to the 6th. Now it says to write the answer in scientific notation, so I have to check and make sure this number is between 1 and 10. It's not. I've got to move the decimal over one place, which makes it 3.3 times 10 to the negative 1, because that was a decimal. And I already had 10 to the 6th. So it's about 3.3 times 10 to the 1/5. So if they wanted to know about how many times bigger it is, this is the answer. Just to think of it in terms of things we would understand, though, if I move that out, that would be 1, 2, 3, 4, 5. That means the sun is 330,000 times bigger than the Earth. It's kind of hard to wrap your mind around
I
it.
expected that to be several trillion.
The sun's not that much bigger than the Earth, but it's still quite a bit bigger than us.
The sun is a mass of incandescent gas.
Okay, we're recording.
Oh, yeah.
All right, number 9. In Russia, the population was 290.9 million people in 2002. The total healthcare costs for the country at that time were 1.7 trillion. This is how you see numbers in the newspaper, or if you're watching the news or looking at a news feed online, they don't write out all the zeros. They're going to say million and trillion after it, and they kind of give you a decimal, which is sort of like scientific notation, but not quite. It says calculate the average amount spent per person on health care. Write your answer in scientific notation. So we need money spent per person. So I'm going to have dollars divided by people. So 1.7 trillion, we need to figure out what that's going to be. So trillion would have how many decimal places?
12.
So I think it's
12.
so 3 for 1,000, 3 for million, 3 for billion, 3 for trillion. So it would be 12. And then 290.9 is not written in scientific notation, so you have to think about it. 290.9 means 290,900,000. That's what that would mean. So we've got to then figure out this would be 3, 6, 7, 8 decimal places. So that would be 2.9 times 10 to the 8th. So if it helps you, write out the number. And if you still have that large number packets that we had before, they have a lot of the millions and trillions and stuff written out. All right, so if I take 1.7 divided by 2.9, I get 0.586. If I take 12 minus 8, I get 4. Is that my final answer?
No.
No, I have to move the decimal over one place. So that's going to be 5.86 times 10 to the negative 1. I already had 10 to the negative 4th. So 5.86 times 10 to the 3rd dollars per person. And then we could actually figure out what that is in real dollars, because I think it was 10 to the 4th until we moved this decimal. Then we had to take one away. So this would be the same thing as $5,860 per person. So the health care costs for that year per person in Russia, in 2002 was a long time ago, was 16 years ago. You guys weren't born yet. $5,860 per person. I will tell you that has gone up.
I'm pretty sure Russia has less people than
well, if in 2002 the lines were drawn a little differently, so I'm not sure.
I guess that would have been when Russia still
I'm not sure.
part of what was the Soviet Union.
I don't know. All right, number 10. Scientists discovered that the size of the Antarctic Ocean is 2,330,000 square kilometers. So that's how much it's covering. How big is the Arctic Ocean if the Arctic Ocean is 3/4 of the size of the Antarctic Ocean? So when you see something like 3/4 of, that means 3/4 times this number. But we're going to put this number.
In science and education.
Actually, let's start just by writing it as a regular number just for fun. And maybe we'll change the answer to scientific notation. So if I'm going to take a fraction times a whole number, I have to turn the whole number into a fraction. So put it over 1. And then we're just going to multiply across. I'm going to use my calculator to take 3 times 20,330,000, being really careful with all those zeros. So 121980000, and then 4 times 1 is 4. So then I can take that number divided by 4. That's kind of a pain in the butt with all the zeros. But I wanted to show you could work this all out and then convert it. So this is my answer not in scientific notation, and this would be square kilometers. And then we can move it, the decimal, over and turn it into scientific notation. So it'd be 3.0495, and we're moving it 1, 2, 3, 4, 5, 6, 7 places. So times 10 to the 7th.
Don't make me do that again.
I know. But this is why scientific notation was invented. It might have been easier in some ways to do. Let me try this really quick. If I put this in scientific notation to start with, then I would have just had to take 3 times 2.033. It would have been a little easier, because I would have had 6.099 times 10 to the 7th over 4, and just take that divided by 4. Oh well. So it would have been a little easier, but that just makes that point.